This is part 4 in a series of videos in which I'm showing how to use this Fluke 9010a to do some fault finding on some electronic systems. In the previous videos I got as far as showing how to run some simple test programs from the Fluke itself, and then I went on to show how to upload some simple test programs onto the unit under test and run those programs directly from the board that was being repaired. I had intended to go on to demonstrating the logic probe in this video, but I've been asked to expand a little bit on the test programs I was using, also to do a back-to-back speed test between the screen test program run from the Fluke and the same program run directly from the unit under test, and also to explain how the Z80 test program worked. So this will be a very quick video, hopefully. If you already know how all this works, then you can probably skip this video. It's just for people that are interested in seeing how the programs work and what the relative speed advantages are running programs from the Fluke compared to the unit under test. Now, speed's not really the point, it's really running programs from the unit under test gives you full control of the target system, whereas you don't necessarily have that using the Fluke. But it might be interesting anyway just to compare the two programs. So what I've done is enter the same test program into the Fluke that we used previously. So if we look at the program, very short program. I've modified it very slightly just to save a bit of time. I'm going to refresh and test just the top layer of the video RAM. That's the one that the REN logo is written to when you boot up the machine. So it's just 4000 hex or 16k decimal of bytes that we're going to write to the REN. So the address we're going to start at is 8020. The buffer actually starts at 8000, but I'll explain why it's 8020 in a few minutes. We create a label, display the current value of the register that we've just initialized, write to the address that's in that register a value of 45. We increment the register, so that increments the address we're pointing to, and then we check to see if we're at the last byte that we want to write to. So in this case it's C020, which is 4000 hex greater than the value we started with. So in other words, we're going to refresh the entire 16k screen, and then we're going to just display the word finished and beep once the program has completed, and that's the end of the program. So I'll move the camera so we're pointing at the REN, and then I'll run this program. Okay, so I will execute this program, and as you can see we've started writing the value of 45 to each of the RAM locations in turn. I'll leave this running and I'll time it so we can do a direct comparison between this program and the one that will run directly from the REN board itself. But as you can see, it's quite slow. It is going to take some time. It'll probably take around 15 to 20 minutes, maybe longer. And the value that we're writing, because we're on the top layer of the video buffer, is the value, is the pixel value represented by the value 45. So in other words, if you look at a single byte and you assume that each 1 in binary for the value 45 in that byte is illuminated, then that's the pattern that we are writing to the screen. And the reason it's leaving large gaps between each row is because it's interlacing the display. So although we're going up progressively through memory, it's jumping to progressive lines for the interlace mechanism that the REN uses to display the data on the screen. There's various reasons it might want to do that. Most usually it's to reduce flicker when the screen is being updated. So I'll leave it running and I'll come back once it's completed the full write, and we'll see how long it took. Okay, that was the Fluke beeping to let us know it's finished updating the screen. According to the lab clock, that took just under 30 minutes. So you certainly wouldn't want to write a game using this method, but it fulfills the purpose. It allows you to write values to the system memory and carry out some in-depth testing. But as I said, it limits you to what you can access on the target board. So what I'll do now is enter the Z80 machine code equivalent of this program, and we'll run it again. Before I do that, I'll just run the machine from its normal startup address, and that will refresh the screen. So we have the normal startup screen. I'll now enter the assembly program and we'll see if it runs any faster. Okay, I have the assembly version of the program entered into the Fluke, so I'll now execute that program, and as you can see it's already finished. So that took probably a little over a second and is therefore over 1,000 times faster than the equivalent program running directly from the Fluke. So this gives you a lot more scope for doing multiple tests. I've used the same test pattern here, but this will also allow you to figure out exactly how the graphics work. You can see in the top left hand corner the first 16 bytes on the display are actually the binary values for our program, and that's why I'm only refreshing the screen from 8020 rather than from 8000. That's to make sure we don't overwrite our program. What I can do now, of course, is go into the program and change the pattern that we're writing to the screen. So I'll do that now. I'll show you the program in a few minutes. So I'm just changing the value that we're going to write to the screen. So I've changed the value. Now, because we're writing individual byte values as pixel maps across the screen, what I've done now is enter a value of 1 for the binary value that we're writing to the screen. So this should give us a series of thin vertical lines if the display works the way that we're assuming it does. So I will run this program again, and as you can see, we do indeed get a series of vertical lines. And you can keep doing this as often as you want. You can also now run the standard program within the Ren, and you get the normal screen at that point in its operation. So it's a very powerful way of accessing the hardware on the unit you're trying to test. So I'll move the camera now. We'll have a quick look at that code in the Fluke to see exactly how it works. Okay, so apologies again for any flicker on the display, but if we look at the program that we've used, or the two programs we've used so far, program 1 is the Fluke version of the program, and it works in a very simple way. We initialize a register with the address that we want to start writing values to on the target machine. We create a label so we can jump back to this point in the program. We display the value in register 1. And when I say display it, I mean we display it on the Fluke display, not on the unit under test. We then write the value 45 to the address that's currently indicated in register 1. We increment register 1 to point to the next address, and then we check to see if we're finished. If not, we jump back and we repeat process and write to the next address in memory. And then once we've finished, we simply update the display on the Fluke and beep to let us know that it's finished the program. Program 2 is of course the machine code version of that program, written in Z80 code. So if we have a look at that program on paper, what we do is we load the DE register pair with a value of 4000 hex. If you're not familiar with the Z80, it's got quite a nice feature. It's very similar to PIC microcontrollers, if you're familiar with those, in that you can use certain register pairs either as two 8-bit registers or single 16-bit registers. The only downside in using them as 16-bit registers is that any operations on them tend not to update the Z80 flags. So for example, you can't decrement or increment a register pair and check the flag for 0 because the flags won't have been updated. So we write a value of 4000 hex to register pair DE, and that 4000 hex is the number of bytes that we want to write to the video memory. Bear in mind this will be executing on the actual unit under test board, not from the Fluke. We then load register pair HL with a value of 8020 hex. That's the start address that we want to start writing data values to. We use 8020 rather than 8000 because this program will be actually written to address 8000, and of course we don't want to overwrite it as soon as we start writing values to video memory. We have a label here so we can jump back, and so this forms a loop. We then load the value 45. This is hard coded here. We could use a register here of course, but we use a hard coded value of 45, or in the last run I actually used the value of 1 to give us the thin vertical line. So this is the bitmap that we're writing, and we're using HL as the address pointer. So in other words, we're going to write a value of 45 hex to the address pointed to by HL, and that starts at 8020. So the first time through it will write a value of 45 hex to address 8020, which, if you recall from the previous video, is the second page of the character RAM on the REN. We then increment HL to point to the next address. We decrement register pair DE because that's what we're using for the counter, and we then need to check to see if we're finished. In other words, has DE reached 0? As I said, it doesn't update the flags when we decrement a register pair, so although this is a valid instruction for the Z80, it doesn't affect any flags. So this next couple of lines is just to check to see if DE has actually reached 0. If you're not familiar with this construct, and it's very straightforward, what we do is we load the D register. Bear in mind DE is a register pair, so it's two 8-bit registers. So we load the D register into A being the accumulator. Then we OR the E register, that's the second of our register pair, with the accumulator. And so that those two steps mean that if any of the bits in either D or E are set, then we'll end up with a non-zero result in the accumulator. So we can then check the 0 flag, which will be affected by the OR operation, to see if we've reached 0 yet in both D and E. If we haven't, we jump back and repeat the process. If we have reached 0, although it's showing halt here, that's not what's in the actual program. If I move through, then when we get to the last step, then the last step is run UUT at 8000. In other words, we load all the values into the memory on the REN, and then we actually execute the program that we've just loaded into it. Once it's loaded, you can then rerun it if you want, because it's obviously residing then in the REN memory, and all you have to do is tell the REN to run from this address, and it will repeatedly run that program. Okay, so that's how this program works. Now, because we now know how the memory is arranged within the REN, it would be very easy for us to write code to create actual characters on the screen. Now, that's not really what we're intending to do here. I'm just doing this out of interest. So if we have this very high-tech system I have here for determining what values we need to write, if we assume we're going to write on an 8x9 pixel grid, so this is our font size, then we can work out what hex values we need to write in each subsequent character line to create whatever character we want, in this case an uppercase A. So I'll now write a quick program to send these values to the REN, and we'll see if we can write a character on its screen. Okay, so I've created a third program, and if we have a quick look through, it's very simple. All I'm doing is writing the binary values that we determined we needed to write the uppercase A, and I'm doing those on subsequent horizontal lines. Now of course, because we're using an interlaced display, they're not consecutive lines, so it's a very quick bit of maths, and it was easy to determine that each line is 400 hex bytes stepped on from the previous one. So all I've done is assume that each row of the character is 400 hex bytes displaced from the previous one. And so as we go through, you'll see that the address we're writing to jumps up in values of 400 hex, but we're actually writing the next byte value on the next actual scan line on the display, not 400 hex lines down. So that's all it does. It just goes through and writes the values we need to write the uppercase A. So I'll move the camera, we'll have a look at the display and see what that gives us. Okay, so if this program works and the REN is operating the way we think it is, when we execute this program we should get an uppercase A appearing in the top left hand corner of the screen. So I'll execute the program now, and as we can see, we now have an uppercase A in the corner of the screen. I'll just move the camera a bit closer in case you can't quite see it. So as you can see, we have a nice uppercase A. So now we know how the REN video RAM works, we know how to test it, and you can do exactly the same thing with any part of the system. You just need to know the address to write to and the appropriate values to write to it. Of course, this particular program was written on the Fluke, but we could just as easily have written it in Z80 assembly and uploaded it into the REN and run it directly from the REN's own memory. So hopefully that clarified things a little bit. If you want me to go into more detail, let me know, but just bear in mind that this is a very powerful tool that you can use once you get the hang of it, and you realise you don't need to limit yourself to just what the Fluke can do directly. You can use it almost as a fully fledged in-circuit emulator and write pretty much any program you want within reason to the unit under test, and that allows you to create very powerful test scripts and to do very detailed fault finding down to the individual bit level on any device on the board that the system microprocessor can access, either directly or indirectly. Okay, in the next video I will get onto the logic probe, and hopefully that will give some indication as to just how powerful the Fluke 9010a can be as a fault finding tool.